The hosts have not yet filled up the attendance, that'd be good time spent. And otherwise, if you want to follow along with the slides, I posted them in the ACM Discord. So is anyone not in the ACM Discord, or they need like a bit or something? And let me know right now and afterwards. Also, that loud enough? That loud enough?
A little bit louder.
Okay.
Sorry,
Okay, okay.
the wind's like blowing my turn.
Yeah, definitely.
No problem. So, yeah, I guess
That sounds good. Okay.
basically today we're pretty informal GM, so we'll just start by sort of recapping what we're going to do this quarter. We'll do with the team that I've already kind of done, and then we'll fill out a social form. We can vote on an activity to do in maybe a few weeks, and then we're gonna jump into some common myths and misconceptions. So we'll ask you guys to just poll you guys, see what you think on these, and then we'll let you know some like reasoning about them. Then we'll move on to a high level overview of quantum computing and like some of what's capable of some quantum properties. And we'll do this at like a very qualitative level before we start like moving into more of the math in the coming weeks. And then finally, we'll start looking at the full quantum computing stack. So let's take a very brief look at like some of what the hardware looks like, and we'll just come all the way up to like, some software and current research tools. If it's still too hard to get at the back, maybe you have to just come up a little bit. This is on space at the front.
Right.
Basically, maybe a quick show of hand, like how many of you guys found us at ACM GM yesterday? And then otherwise, how many of you guys found us at like the engineering working day a few weeks ago? So just to recap some of what I'm sure you guys have already heard, we're trying to make each of our workshops as hands-on as possible. So we're gonna have a coding throughout. There'll be like we'll intersperse our lectures with slideshow with this coding and the Qubit platform. So you'll see that in the attendance form, we like ask for your email, and so we're just gonna add you to a like course that we made on Qubit's platform called Qubit, and there is where like the coding is gonna happen. You'll have access to real quantum computers there, and it'll just be some like, more interactive stuff. So in addition, like once we get started with the workshops next week, after the 1 hour workshop session, we're gonna have a sort of office hours portion. So the reason for this is because we believe that learning quantum can be pretty hard in the beginning and pretty unintuitive. So we just want to clear up any misconceptions that might arise early on. And yeah, here at the quarter, we're also this is a pretty new initiative. So if you guys have any feedback, we would love to hear it. We've already done some brief introductions, but I'm Victor, second year EE.
My name is Ian. I'm a fourth year material science major.
Yeah, and I'm Narayan. I'm a second year computer science major.
So yeah. For reference, this is going to be the beginner track, and the idea is that I'm hoping to expand to include an advanced track and maybe some projects later on in the winter, where right now main focus of these workshops is it's just the learning, and we'll try to add interactivity as we grow. But once we have this background built up in the winter, we're going to try to move to some real projects, hopefully contribute to some open source code over at QGrade and stuff like that. So here's a bit more of an in-depth agenda. I don't know if it's a bit too small and you guys can follow along on your phones or laptops, but next week we're going to start by introducing all the basic quantum gates. So there's like the NOT gate, the controlled NOT, the Hadamard, other gates that you may have heard of. And the theme for this workshop is we're going to try to show you that quantum computing is not too scary. So even though it may seem like really abstract and may have a lot of capabilities that are hard to understand, we're going to basically try to make it as concrete as possible, try to introduce only a few features, and just show that like it is approachable and it's not too dissimilar to classical computing in some way. So we're going to basically implement some basic classical logic gates, such as like NOT or stuff like that in quantum gates. And then after that, now that we've sort of like dipped our toes into quantum and some of the formalism, we're going to start talking about why is quantum like actually cool. So what are some like uniquely non-classical capabilities that quantum computers have? So for example, we'll start talking about like phase, the block sphere, and all of that in week 2. And then we'll introduce the quantum circuit model. And finally, we'll do a worked out example of quantum teleportation. And you guys are going to implement this in Python notebooks. So after that, we're going to start, since we have like all the quantum, all the foundations built up now, we're going to move to a basic algorithm known as the H2 algorithm. And we'll basically get into the theory of how this works. And again, we'll implement this in the notebook. And so, yeah, I guess the theme of this one is like quantum computers can solve some like contrived like toward problems better than classical computers can. And then after this, we'll move into the sort of bigger name algorithms like Grover's algorithm, which is an algorithm for search that is faster than like we can do classically. And I think this is pretty unintuitive because you can imagine like if you are just searching through an unordered database has like n items and you want to find like one particular item. On average, you might expect that you have to go through like half of them or something like that to find a solution. But in quantum, we'll see that actually takes like order of root to n. So if you have like 1 million items, it scales only as like proportional to like 1,000 of the items you need to look through. Like some like rough heuristic stuff. So we'll dig into that, like why that's true, and we'll implement that across 2 workshops. So the first workshop, week 4, we're going to be looking at the theory, and then in week 5, we're going to look at the actual implementation of this Python. And then finally, we're going to move to like arguably the biggest name quantum algorithm. So this is Shor's algorithm. This is what breaks up part of the topography, and we'll get into like how it works, and again, try to like implement it at a simple level and even run it on quantum computers that we have access to through QBraid. So theme of this, as we scale up, is now like we're trying to show that quantum computers can actually solve important and useful problems and, for example, break modern encryption. That's the idea. If you guys have any questions, feel free.
Yeah.
Are you guys like gonna keep restarting the curriculum every quarter, or are you planning to like kind of keep progressing throughout the year?
So this is like the very first quarter we've ever done this. So right now we're doing the beginner track, but as we get more people interested, more people involved, we want to include an advanced track as well. So we'll have this next quarter as well, and an advanced track for people who already came this quarter or maybe a bit more advanced in quantum.
And like, also like, will there be like officer positions that you can apply for to like maybe teach the new people?
Oh yeah, definitely. It's only us 3 of us so far, so.
From that later in this quarter, as people dig through this the workshop series, we'll open that up.
Yeah. Oh, by the way, we want this to be pretty informal, so if you guys have like any questions, feel free to speak up.
This is a fairly big worry of most people. So the expected math and physics I might be expected to know before we can do this. And we're really trying to make it so that you don't need to know any advanced math and physics. So not even much linear algebra. We will have to ultimately use linear algebra and its machinery, but we're only going to try to like stay at a pretty basic level. So we'll introduce anything that you need. And then again, the goal is that we have this off hours portions afterwards. So maybe if your math background is a little bit weaker, we can try to shore that up with you afterwards. But otherwise, like this is most of what we'll need with the quarter. So like if you know this, then you'll be in like very good shape. So just basic linear algebra, like what's a matrix? How do you do matrix multiplication of other matrices? How do you multiply a matrix by a vector? What is a dot product? How do you calculate that? It'll be good if you know some summation notation, like sum over I and whatnot. That'll come up with like Grover's things later. And then also if you complex numbers, just what they are, how you can work with them. Is anyone like pretty unsure about any of this, or like it's kind of a reasonable background for everyone? Yeah.
Like conjugation and norm, I guess.
Sure. Yeah, I think we'll probably briefly touch into that in week 2 when the actual test showing. But those are pretty simple concepts, so I think you'll get them the same. Otherwise, do most people like roughly know what a matrix is, or just to like scope this out? Like raise your hand if you don't know what a matrix is. If you've never done any algebra. Sure, right. No worries.
Don't worry.
We can, yeah, if you need like a refresher or something, we can talk about it afterwards. But yeah, I think everyone should probably be fine. So now from social, just another QR code, another very quick Google form. Sorry for giving you guys so many, but basically this form is just to pick out the week that we're gonna have the social and also the activity. So I just put in a few kind of generic activities like KBBQ, boba, like other things. But if you guys have any better idea, feel free to just like say it now or like put it as other in the form and we can vote on this throughout.
Do ACM people just like QR codes?
Yeah, it's like the best way to get like data and responses from a lot of people. So yeah. Just go on to the next slide. All right, so for today's GM, we'll actually introduce quantum computing to you guys. Um, so as you guys all know, there's been a lot of hype surrounding quantum computing recently, you know. These are two of the craziest headlines I saw, you know. Google claims its new quantum computer provides evidence that we live in a multiverse. I know, right? And teleportation achieved between quantum computers in a world first. I mean, I don't know about you guys, but when I first saw these, I was like, what the heck, man? So
I mean, how much of it is like overstated?
I'm glad you brought that up. That's actually what we're covering today.
We'll actually see this in 2 weeks. I'll compare.
I mean, like physical teleportation, not like inference of information.
Yeah, so this is only referring to like information being teleported.
Yeah,
so I'm not gonna
that's-
say anything.
Yeah, so I'm sure you guys have a lot of questions. So first thing I'm gonna do is summarize what is and isn't overblown about quantum computing. And then we actually want to clarify and explain what quantum computing is and what it is actually capable of. Give you a more grounded view of the whole field. And then I'll give you my 2 cents on why I feel like quantum computing is valuable. And then Naren will take over and present what is actually being done in the field today. So this is our first section, busting quantum computing myths and misconceptions. So quantum computing will be able to solve every problem. This is our first potential myth. What does everyone think? Raise your hand for yes. Okay. Raise your hand for no. All right, this one was kind of obvious, but yeah, this is false.
You needed the loud incorrect buzzer sound effect.
You know, that's what I said to him, but he wouldn't let me. Yeah, so unfortunately, quantum computing is not some holy grail of computing. It is only good at solving a limited number of specific problems, but the reason why it's like actually like super sought after and people care about it is that some of the problems that quantum computing actually can be used to solve are very, very important, specifically to like computer scientists. I'll briefly mention a couple of them, but like we'll definitely delve into this much more later. Like he mentioned earlier, like the unstructured search problem, and there's a whole category of problems called NP problems that quantum computers are very, very good at. If you know what that is, that's awesome. If you don't know, we'll definitely cover it in later workshops. The second potential myth. Quantum computing will replace classical computers. Show of hands for yes. Show of hands for no. Once again, I felt this one was kind of obvious, but yeah, this is also false. So yeah, as it turns out, quantum computing and classical computing are actually two different regimes. They both have their own strengths and weaknesses, and they have various trade-offs. A similar comparison I could give you would be boats versus cars. They're both very, very good at what they do, but if you try to like, you know, drive a boat on the road, I don't think you get very far. Similarly, there's a lot of problems that I feel would be very, very impractical to solve with quantum computers that classical computers do very, very well. For instance, like uh, rendering images, like with GPUs, or like even as something as simple as like operating systems code, you know. Using quantum computers to do all that, I feel like would be kind of a waste of resources and also very inefficient. Does anyone have any questions or?
Here you might like hear the comment or like, and I run to my quantum computer, and it's like not what they're like really made for, but we can maybe talk more into like what they can do.
Yeah.
How would you generate the image?
Generate the image in quantum computing?
No, like
No,
how do
that,
you
yeah.
get that image on the slides?
Oh, like are you?
It's really AI generated for no reason in particular.
Oh, I didn't notice. I mean, it says AI on the corner, so
Oh, I'm blind. I'm sorry.
okay, no worries.
I have glasses.
And our third potential myth: quantum computing will break public key encryption, and all my private information is screwed. Hands for yes. Okay, a bit more hands. Hands for no. Okay, so this one's actually true, kind of. So, I think we mentioned it earlier in a previous slide, but there's a very famous algorithm called Shor's algorithm that makes factoring large integers very, very easy. Unfortunately, this breaks RSA encryption because what makes RSA encryption hard, like hard to break, is that they use the fact that factoring large integers is very, very time consuming and it's challenging for classical computers. So if quantum computers make factoring large integers very, very easy, then like, it might as well not be there. Yes?
I don't want to ask a question if we're going to cover it later, but like, wait, what is factoring large integers and RSA encryption?
Oh, yeah, absolutely no worries. That's a good question. Factoring large integers is just like you have like a really, really big number and you want to figure out its prime factors, right? I don't know the exact specific details, but I think what RSA encryption does is that they use like a really, really large, like I think like 2 to the 200 digit number, right? And then they find out uses prime factors and then like they intertwine it with like another number. And then to decrypt it, I think you kind of have to like factor the really, really large integer. Sorry, I'm not an expert on this. I think that's like a high level overview. Yes?
I thought TLS 1.3 has like safety nets against UC brute forcing.
Mhm.
So in general, there's like sort of post-quantum photography, which you're interested in. So there are some like mechanisms of, again, including data that you can prove quantum computers aren't able to crack. So there are problems that are also very hard for quantum computers. You can use these sort of cryptographic problems to encode your data. So the government is trying to like transition to these eventually because the quantum computers progress is constantly being made. But yeah, these things do exist.
Yeah. However, a good caveat, something that's reassuring, is that unfortunately, or maybe fortunately, quantum computers are not actually advanced enough yet to run Shor's algorithm. Right now, I think we roughly have 6,000 qubits in our best quantum computers, but experts estimate that we need roughly 1 million qubits to actually get it running. However, some more bad news. There are some bad actors out there that are storing data on the internet so that they can decrypt it later once quantum computing actually like Shor's algorithm actually becomes possible. Yes?
What is qubit? Like,
Thank you. That's a really, really good question, and we will get into it. That's like one of the main things I want to address. I think it's in this section as actually. So what is quantum computing and what can it actually do? So what is a qubit? So a qubit in a nutshell is like the fundamental unit of computing for quantum computers. They're kind of like classical bits in that they can take on the pure states of 0 and 1. However, one big difference that they have that make them different from classical bits is that they can also exist in something called a superposition, a blend of 0 and the 1 state, where the outcome of measurement is determined by probabilities. So to translate that into English, basically, when they're in the superposition state, they actually can become either 0 or 1, depending on like a probability distribution. Like if you measure a qubit that's in a superposition like 1 billion times, right? For all those 1 billion times, you're not going to get like 1, or like for all those 1 billion times, you're not going to get 0. You're going to get like 50, maybe for 50% of the time, you're going to get 0. Maybe all the other 50% of the time, you're going to get 1. It's non-deterministic. And the probability is actually determined by a probability distribution that is kind of encoded inside the qubit. And as the second big property that makes, oh yeah.
Just the classical bit, because if you did it a billion times, it'd always be the same thing.
Yeah. For a classical bit, thank you for bringing that. I think that's a good point of clarification. Classical bit, if it's in the 1 state, and if you don't like use like an actual gate to change it to 0, no matter how many times you like measure it or like check its value, it's always going to be one, right? Uh, that's like one of the big differences between quantum computing. You don't have to do anything, you don't have to change it, but if it's a superposition state and you like measure it like a bunch of times, like it won't always be one value. It could be one of either two values. Yeah.
So is that distribution with qubit constant for every single qubit, or is that different?
Not at all, not at all. You can actually manipulate that distribution. That's actually one of the great strengths of quantum computing. We'll definitely delve into that a bit more later once we actually start into workshops. But I just want to give you guys an idea of like what kind of makes it different. And did you have a question?
Not me.
Okay. Oh, yeah.
Entanglement, if you know the spin at one point of one, you know the spin of the other that's entangled with, right?
Yeah, that's kind of the idea.
Roughly, I don't know.
Yeah. No, I think you're absolutely right over there. So the second big property that qubits have is, as he just mentioned, entanglement. Um, Once again, this is just a GM, so we're only giving like a very like surface level review, and we'll definitely go into this once we actually get into the workshops. But in a nutshell, entanglement is a property that happens when there's more than one qubit, right? So if there's more than one qubit can get entangled with another qubit. And if you measure one qubit, right? So like it's in a superposition state and you measure it to be one, that actually affects the probability distribution of the other qubit, right? So for instance, let's say you have two qubits that are entangled, one of you measured to be one. For some reason, measuring that qubit to be one could make this other qubit always measure one, right? Yeah. Yeah, of course.
You have access to how far away are cues from each other, because like entanglement is very sensitive, right? So it's like super super.
Actually, like, doesn't matter so much relative to like, only relative to like your interaction strength, right? So I guess the point of like the constructed maybe these quantum devices is that they're trying to find a place that they're going to pack it as close as possible. So when they scale up, it's not like a quantum computer that takes up the size of a football field, which is like what is currently projected, like the size you need to break for that. But I guess to give you a actual number, in some devices it's low nanometer scale, some of them today, and 200 nanometers between qubits, and some bigger devices much higher, below micrometer separation. And so if you don't know, like nanometer is 10 to the minus 9 meters, so it's really very small, and the micrometers is 10 to the minus 6.
Yeah. Also, I think it depends on like which regime of like quantum computing devices they're using, which Naren will get into. So how is quantum computing actually done? So at this moment in time, quantum computing, at least the practical version of it, is at a very low level. So what does that mean? Back in the 50s or so, classical computing was also at this sort of similar low level where we actually performed operations and gates on the qubits themselves, on the bits themselves, right? If you see this image on the top right over here, this is an example of such a low level operation on regular bits. You have these three bits over here, XYZ in the register, and then you see the classical AND gates acting on these bits, and yeah, you see the output over there. So the way quantum computing is done right now is actually very similar to the way classical computing was done at the bit level, Similarly to like this bit level computation, we have over here a register of qubits, right? And then we apply a series of quantum gates on them, right? And then the big difference is that at the end of after applying all these quantum gates, we measure it to actually extract the information. Sorry, I feel like I should have like mentioned it before, but like measuring a bit forces that qubit into the state that it got measured into. For instance, let's say you have a qubit in an entangled state, you measure it, and if you get a 1, that qubit is permanently in that 1 state now until, once again, you artificially change its value using a gate or something. This is also like a kind of like one of those weirdness of quantum computing, and this stems from like the physics of quantum mechanics. As much as I'd like to delve into it, that might be out of the scope right now. So yeah, so what is quantum computing actually good for? It's good for problems that require a high number of compute/parallelism. More precisely, it's good for problems in which classical computers are forced to do kind of like a brute force type approach because they just don't have a better way of solving that problem. A good thing about quantum computing, like, is that because of these special properties, clever algorithms can leverage the properties I mentioned earlier, like superposition, entanglement, to gain crazy computational efficiency. Like Grover's algorithm we mentioned at the beginning can get like a square root speed up, but Shor's algorithm, the reason why we say like it'll break RSA encryption is because it speeds up the integer factorization problem by an exponential amount. Uh, the second big use case for quantum computing is that the built-in quantum properties inside the qubits allow for efficient simulation of quantum systems. Quantum systems being like the stuff you study in like physics or like chemistry and the natural sciences. Um, a big thing about these quantum systems is that they're very, very challenging for classical computers to simulate. Um, especially if you like want to simulate how they move with time, right? So uh, qubits naturally have these quantum properties built in, so they don't actually have to do the extra calculations that a classical computer would have to do. And that actually gives it an exponential speed up over classical computers. This was actually the original motivation for quantum computers all the way back in the 1960s, I think, where the physicist Richard Feynman like proposed the idea of quantum computers. It was to actually simulate quantum systems, and hopefully we get there. To give you a bit more concrete idea of like what this would look like, let's say you have a molecule of like 300 atoms, okay? For a class computer, you'd have to do maybe on the order of 2 to 300 calculations to simulate that molecule accurately, as opposed to quantum computers, which only need maybe 300 qubits. I'm not sure if these are the exact numbers, but like it encapsulates the idea. Okay, now this is the part where I try to convince you to study quantum computing and why it's awesome. First of all, I feel like studying quantum computing exposes you to very unique and elegant problem solving. So it's kind of like extra tools in your toolbox. You'll gradually pick up like different strategies that quantum computer scientists use to solve problems. And I feel like it gives you a fresh perspective of problem solving that may not be available to classical computer scientists. Like just the way we tackle problems, the way these algorithms are constructed, I feel like are very unconventional without knowledge, ever seeing this kind of stuff beforehand. And the second big reason, a lot of you math nerds like me will agree with this. We'll see the beauty in this. I feel like quantum computing, the theory behind it and all the notation and everything is incredibly self-consistent and elegant. Um, I think Victor mentioned this earlier, but it's heavily built into linear algebra, and all those theorems, all that beauty is built into quantum computing. Secondly, I believe quantum computing tackles some extremely important problems, right? As we mentioned earlier, fast integer factorization screws over RSA-based encryption, right? That's a pretty big deal because we have so much data, our private information all over the internet. And some of you who are a bit more studied in the computer sciences might recognize this word, NP-hard problems. Quantum computing can actually be used in its advanced applications to give efficient solutions to NP-hard problems. NP-hard problems are a special category of problems in computer science that are a very, very big deal. And the fact that quantum computers give us the best possible solutions available right now is kind of mind-boggling. And lastly, the original motivation for quantum computing, they give us a massive advantage in simulating quantum systems. And if we're able to do that efficiently, dude, the amount of progress we'll get is insane. We could discover any material, all like basically any drug, anything in like any protein, whatever. Yes.
A question I have, just asking, one big application that I understood about, or like, it's solved with an NPR problem. An example would be like, they actually seem really relative to things like unsupervised learning, where like k-means clustering is
Yeah,
an
yeah.
NP-hard problem. And so that's is that like an example of something that gets solved because it's NP-hard?
I think so. I don't think we have enough qubits to actually like get some.
Yeah, not
Yeah.
theoretically, but like theoretically.
Yeah, definitely.
Cool.
Other question?
Oh, yeah.
How do they like solve these like really hard problems? Like, do they just keep going until they find it? Do they brute force it until they find a solution, or is there some sort of like?
They only so if a problem solves in non-deterministic polynomial time, what that means is it scales so massively as as inputs increase that it takes too long to run the algorithms. They can only currently a classical computer could only run an NP-hard problem on a really small data set.
And it's like for the quantum computer, to address your question, for some of the problems like for shores, where classically you kind of do just have to brute force like various primes and see what factors until you're a big number. There's actually something cutting structure within this problem that you can utilize. And that's what like quantum uses to get this exponential speed up. It's actually generically like in quantum, it's hard to get such drastic speed ups, but otherwise, as we'll see in Shor's in Grover's algorithm, right? Even when like there isn't a sort of structure, quantum like search is just generically faster than classical search. And so that allows you to search for solutions to these hard problems more quickly than classically. And so we'll see how that works later. It's like kind of brute forcing, but like, not really. There is like some specialized quantum algorithm that does it faster.
Yep. Oh, are you? Oh, sorry. I don't. My bad. Yeah, and then another big reason why I feel like quantum computing is worth studying is that there's a lot of money involved. So I think the most recent statistic I've heard is that governments around the globe have invested roughly $55 billion already into research in quantum computing. And that's not even including like the private companies like IBM, Google, or whatever that are based in the States that pour maybe even twice that figure into quantum computing research. Secondly, this is kind of a joke, but not really. Quantum computing complements AI with quantum machine learning starting to take off as a field. So ChatGPT will help you keep your job. And I'll hand it off to Naren.
Okay, so this next section here, we're just talking about hardware and software layers, which basically is just what do people actually do with quantum computing currently. So the first thing I want to give you guys is the quantum stack. So this is just like an explanation of what are the different types of things that we can do in quantum computing right now. So let's start with the base of the quantum stack, which is quantum hardware. So we have these things called cryogenic systems, which are basically just like kind of big fridges. And we have lasers and we have photonic devices. And these are a couple of different ways that companies currently implement quantum computers. And I'll get into the specifics of those in later slides. And then on top of that, we have the actual qubits, which we talked about previously, and we have the physical qubits that are built into these computers. Physical qubits are actually pretty fragile. They're very sensitive to noise. So that's why we have these cryogenic systems and things like that. And when I mean noise, I mean like stuff from the outside. So other like waves and stuff like that. And because of that, we have this layer on top, which is quantum error correction. And what quantum error correction does is that it detects these types of noise and kind of fixes them from a software standpoint. Stuff like the fridge is like something we can do in the physical world to solve it, but quantum error correction is something we can do on the software side. And then we have these things called logical qubits. This is actually where my research was in, which basically is all of these error-corrected qubits with their defined operations. So for whatever problem that we are trying to solve, we would have these logical qubits. And then on top of that, we have QIR, or the quantum intermediate representation. If you've taken a class on assembly before, that's kind of what this is, but for quantum computers. It's for any type of hardware, and it's just pretty general. And then on top of that, we have quantum algorithms. These are really like purely software. They're kind of like the abstract solutions to these problems. And stuff like Shor's algorithm and Grover's algorithm, stuff that we get into in this course is what is mainly in this quantum algorithm place. So who's building quantum computers? We talked about Google and all of like the private investments. So as I was talking about before, they are implementing quantum computers in different ways. So we have IBM, Google, and Rigetti, and they're doing superconducting qubits, which was like that fridge thing that I was talking about. They have this kind of cryogenic fridge, and they have the quantum chip in a circuit, and it's kept at near zero temperatures in order to reduce noise. Yeah, go.
It's power intensive, right?
Yeah. It is pretty power intensive, and I think that's why some people are like that's why there's a lot of different ways of doing quantum computing. Some of them are less power intensive, some of them are less accurate, and so on. Yeah. And then we have IonQ and Quantinuum, and they use something called trapped ions. I'll also get into this a bit more in detail, but basically what it is that we have atoms representing the qubits, and they're held by electromagnetic fields, and they're controlled with lasers to do the operations we want them to do. This is a bit slower, but it is much more accurate than some of the other methods that we have. And then we have D-Wave, and they use something called quantum annealing. It's not really a universal quantum computer. It's actually being used to solve real problems today, like optimization problems specifically. And then we have Microsoft. They're pursuing topological qubits. This is something I'll also cover in a later slide. It's still in a very early research kind of stage, but it has a lot of potential to be like the universal quantum computer because it has a potential for stability and scalability, which are both really important and things that we still want. Yeah. So I'm just going to talk a bit more about the superconducting. So in superconducting quantum computers, like the ones that from IBM, Google, and Rigetti, qubits are kind of like tunable circuits. You can think about it like tuning a guitar string to the right frequency. In this setup, there is the ground state and the excited state that represents the quantum qubit states of 0 and 1. You can think about this like, for example, a ball, when it's on the ground, it has some potential energy. When you raise it above the ground, it increases its potential energy, just like simple physics example, and you can think of it like that. And the chip itself for superconducting qubits, like I talked about, sits at the bottom of this fridge, which is actually at 10 millikelvin, which is 100 times colder than outer space, to put that into perspective. And at that temperature, we can send in microwave pulses from outside the fridges in order to manipulate the qubits to get them to do what we want and solve all these different problems. And you might ask, why do we want to keep it this cold? This is to minimize something that we call decoherence, which is basically just meaning we're preventing any unwanted noise and disturbances from the outside world. Yeah.
I have a bunch of superconducting computers set up at UCLA, so I think like building just tagged over there, E4, E6, somewhere there. There's just like a bunch of them in some labs. So UCLA is a great place to be for general quantum research. You have a lot of research.
And then the next one we have is ion traps, which IonQ and Quantinuum do. And here the qubits are represented as individual ions, like which are charged atoms, and they're held in place using electromagnetic fields. And these ions actually float above the surface of the chip and don't actually physically touch anything. And this is why they are so stable. And in order to manipulate their quantum states, we use lasers and sometimes microwaves also to flip and rotate these ions. And because of this level of control, the ion traps are some of the most accurate qubits that we have today in the quantum world. There's also some other challenges, though. It's not all great. The operations tend to be quite a bit slower compared to other methods. And also, these require really large vacuum chambers, which, again, are expensive to make. So, yeah. And what are researchers currently solving today? So the most important thing is that, like I talked about previously, qubits are super error prone. Like ion traps use the electromagnetic fields to keep them in place. Superconducting uses super cold temperatures to cool them, but even that most of the time is not enough. We still need to look into different ways to correct these errors. For example, Microsoft has their Majorana 1 project, which, like I talked about before, is the topological quantum computing. I don't want to dive too deep into the physics of how this really works, but basically what it is we encode the qubits in special particles that Microsoft developed called Majorana modes. And this information is protected from a lot of the noise that we would get from other types of quantum computing. And if this approach is successful, it could lead to really reliable qubits and less error-prone qubits, which is really good and a huge breakthrough.
Yeah, hopping on that real quick. I kind of just want to put into scale like how quickly these quantum computers lose information and why it's such a big problem. You might be thinking like, okay, sure, like maybe in like few minutes, few hours, like your calculation decays, like it's not useful. But like actually the scales are much lower than that. So in reality, like maybe a decade ago, we were talking like nanosecond scales, all your information is gone. So again, like that's 10 to the minus 9 seconds. And that sort of scale, like you can't really do anything, right? So current day, like state of the art, coherence times in some popular devices, like superconducting devices, which Ryan talked about earlier, a good like sort of lifetime for them, you can think of it as like high microseconds or like low milliseconds. And again, like, this is like really, really fast, right? So like your information is gone that fast. You're trying to do gates, do computation faster than you use it. And then that's why we really need these logical qubits, this quantum error correction and all of that. Like fundamentally, just really hard to isolate these quantum systems from like the tiniest perturbations from outside. And there are some systems that are a lot more resilient. So like trapped ion, they can maybe like hold for much longer. Like spins, they've been held for like hours, these quantum states, but in general, it is like really, really fast.
So with you would act so one barrier could potentially be just measuring things fast enough, right? Like recording input or outputs fast enough, right?
Yeah, I think like in the end, like when you're doing this measurement, electronics are actually really, really fast to tune out.
Yeah.
So measurement is not so much an issue. It's more so that like it just decays before you can apply enough
Before you can do
operation.
like any law.
Yeah.
Another thing is we want to scale up. To do anything truly meaningful with quantum computers, we actually need quite a lot of qubits. And the issue is, again, back to the error thing, is that for every one useful error-corrected qubit, we need around 1,000 physical qubits just to do the error correction technique that we have today. So that means we need to build a machine with thousands or even millions of qubits if we want to solve real world problems. And these are really, really expensive. And we need to find a way to do that efficiently, not just in terms of hardware sizes. For example, like a superconducting computer, probably like that thing back there, probably around the size of that, even bigger at times. So we need to figure that out, but also it needs to be cost efficient, it needs to be energy efficient, and just in terms of like how long it takes to build. And then the last thing is error correction. This is more on like the software side. Error correction isn't just about, it is about recognizing when these mistakes happen and correcting them before they ruin the computation that we are trying to do. It's very similar to how we do it in classical computers, where we have like error detecting codes and things like that. It's very similar in quantum computing. We need like these clever little algorithms that protect the information. But this is a bit harder since measuring qubits will collapse its state of like when it's in superposition. Yeah. And then the final topic is new algorithms and new applications for quantum computing. Researchers are always actively hunting for problems where quantum computers can do something that classical computers struggle with. Which, for example, is like optimization problems. So that's something that quantum computers are pretty good at. These are called quantum advantage problems. If you remember that headline that Ian showed, Google was claiming they had quantum advantage. It's something where classically, like with the normal computer that what we have today, it's really hard to do, like an NP hard problem, but a quantum computer would be much faster at it. Some of these examples include factoring, like we talked about before with Shor's algorithm. It could be simulation, like simulating molecules and things like that, and then optimization problems. And then the QAOA, that is a current quantum algorithm that people use to solve optimization problems. And there also is that big open question, what are some new real world applications of quantum computing? And how can quantum help us solve that? And that's something that researchers look into every day, especially even at UCLA as well. Yeah. And I think that's it for this meeting. Just next week, we're going to go into Brockhet notation, which is pretty important for quantum computing. And we're going to talk about an introduction to quantum gates, and then we're going to start with our first little coding task here. We're going to code classical logic gates with quantum gates in Python. I think the first thing that we'd want you guys to do is actually sign up for a QBraid account. This is how we're going to be, we're going to send you guys all like the Jupyter notebooks, and you guys can follow along in lecture next week and complete little coding exercises as we go along. So www.qbraid.com, just make an account with, I believe it's fine if you use your personal email. It should not matter which email you use. And then have that ready by next week because we need to invite you to the like organization, I believe.
One last thing. I don't know how people's schedules are like. I want to do we can do some other social activities like besides the more dedicated social. So if you guys want, we can do a Boba run after the meeting next time. But maybe you can purchase if we do a show in, if you would be down for that next time. Just to engage interest. Yeah, so we can probably do this next time.
Cool.
So again, try to do this. If not, we'll be sure to follow up through email and put this in the ACM quantum Discord channels. So don't worry if you forget about this. And then yeah, we're just excited to start the workshops and to see you again next week. Yeah, thanks for coming, everyone.
Same time next week.
Yeah.
Yes.
Thank you so much.
Thank you. You guys want to say?